So, for this to be an expansion parameter, a valid expansion, we have to have some assumption about this integral, right? So what is the validity of our approximation? So for the validity of our approximation is going to be if N over V has to be much, much smaller than d cubed r f of r inverse, right? Now, for the Leonard-Jones potential, this thing, you can show that this thing has the form of 1 over approximately 1 over r cubed, r naught cubed. So this statement is saying that the volume occupied by each gas molecule or the average volume occupied by each gas molecule which is this number, right? 1 over this number is much greater than r naught cubed. But what is r naught cubed? R naught cubed is the equilibrium distance, right? Or equilibrium volume. So, remember that if our potential is of this form, sorry, this is not the best picture, is of this form, this distance is r naught. So, if you have two particles very close to each other, such that they're there's a lot of, they are as close as they can be, then their distance will be r naught, and then another particle r naught. So what this is saying is that the gas law is valid as long as the distance between the molecules is much greater than r naught. But this situation where the distance between molecules is r naught has a name. It's called the liquid phase. So what we are saying is that our approximation is valid for densities much lower than the liquid case. Okay. So there's nothing really very much surprising there. Okay. So any questions? Because I think we're in the last stretch.
So would you scroll up a bit? at the double summation sign of the equation.
Yeah.
Yeah. How did the double summation sign come from the previous slide?
Oh, right. So it comes from multiplying, these guys. So if I have, say, suppose the number of gas molecule is only two, right? Then we have one plus F. Say the number of gas molecule is, say, three. Then this factor is going to be one plus F12, one plus F13, one plus F31. So if I now multiply this, I get 1 plus F12 plus F13 plus
Oh,
F.
I got it.
Sorry,
So
yeah, 3, 2.
that
Sorry,
is
this is
the
not.
summation
Yeah, yeah,
of
yeah,
the
yeah. Sorry.
multiplied terms.
Yeah, exactly. Yeah.
Okay.
Okay.
Sir, I had a question regarding the Hamiltonian. So, in this case, we are having n particles, but in a previous lecture, we wrote down the partition function for a single particle, isn't it?
Yeah, exactly. Here we cannot
But
do that.
yeah, but my problem was then, even in the single particle case, we have this notion of temperature, playing around. It is kind of confusing. Like temperature in case of one particle, like how would we come up with an interpretation of it?
Temperature in case of one particle is, so you're saying that, yeah, you can have, you're basically looking at what are the possible energy of the particle in, you know, within a given thermal environment, right? Why is that confusing?
Mm. Because like in the thermodynamics section, we learned to uh, do with the concept of temperature for many particles and not for a single one, I guess.
Uh,
But if we say like a thing from the perspective of a like a canonical ensemble, then I
yeah,
think
I
the
think it's more
confusion
from a point of
resolves.
view of the canonical
I
ensemble.
see, I see. Okay.
Yeah. But that's a very good observation, because what you're saying is that fundamentally, temperature is a measure of the kinetic energy of the, of the gas. So, for example, if I put, if I take, say, one gas molecule and put it in some vacuum, then you might ask, does the vacuum have a temperature, right?
Yes.
And so here, I think the idea would be, if there is radiation in the vacuum, then probably there's going to be a temperature. So yeah, no, that's a very good question. I think conceptually, it's a good question, because uh, you know we are saying that a single particle does experience temperature, but it's kind of a bit contradictory, because if it's not interacting with other particles, then where is that temperature coming from? Because you know uh, because our understanding of temperature is that it is due to the kinetic energy, average kinetic energy of the gas molecules, right? That's what you're asking.
Yes, sir.
Yeah. No, I get it, but and I think it's more of a formal approach at this point, that this is how it works. That if you were to think of a gas molecule by itself, then even if there's, even if you're looking at the at non-interacting, like the ideal gas law, the thing is there is still interactions, and it's just that, or that, you know, that interaction but that somehow the interactions are not dominating. Yeah, the I think the canonical ensemble kind of, you know, leaves out the mechanics by which
Yeah, I was thinking if we
particles.
start with the canonical ensemble, then it shouldn't matter much whether it's a single particle or a multi-particle system. Like, should it?
Exactly. So the canonical
Yeah.
ensemble is more of a prescription rather than a description of how that gas got its temperature.
Sir,
Okay.
we define temperature by like the definition 1 over T is del S del E, right? Like del S over del E.
Exactly. Yeah.
So
Exactly. The temp. Yeah.
for a single particle, like there's only one what they say, one configuration uh, for only a single particle with like fixed energy. There's
Yeah.
only a
Exactly.
so like then del S del E is going to be zero. So temperature is going to be infinite. Is that logical? Like entropy doesn't change for a single particle. So 1 over T is 0 and T becomes infinite.
Yeah. Obviously, this is not temperature.
So
The
I
idea
mean
of
we can
temperature is not.
define like it shows that we can define like 1 over 0 is undefined. So I guess we can't define it.
No, I don't think we are. I don't think they're saying that we cannot define temperature. What I would say is that um, we are not using the canonical ensemble to define temperature.
I always used to think that temperature was an emergent quality of like many particles. So is it even possible to say that a single particle should have a temperature?
No, that's what I'm saying is that a single particle cannot have a notion of temperature.
But we can use energy interchangeably with temperature for a single particle, right? Because it has energy, even though it's a single particle.
No, energy and temperature are not the same thing. They're related, but they're not the same. Okay, I think what is happening here is the following. When we are looking at the partition function of a single particle, we are assuming that it's immersed in some environment where there is a temperature. And if we have n such particles such that they're not talking to each other, that's how we get the partition function of n particles. So, you know, because in the definition of the canonical ensemble, the temperature is there. So, you see what I mean?
Yes, sir. I mean, there is a reservoir, even if there is a single
Yeah.
particles.
Yeah. So the idea of temperature precedes the definition of the canonical ensemble.
I understand now, sir.
Yeah, I mean, I think it's a valid question, but it's not a question that can be addressed in the context of canonical ensemble because we have already used that concept to define the canonical ensemble. So the question has to be asked outside the canonical ensemble.
Sir, I have
Okay?
a confusion in the equation. Would you scroll down a bit?
Sure.
Uh, up, you crossed it a bit upward. a bit upward again. Before the Z.
Yeah.
Yes, so R12, what did you do here? R1 plus R2 divided by 2. Is this the average?
This is the center of mass coordinate of two molecules.
And about the Vn minus 2, so why are we treating R1 and R2 differently so that we didn't include them in the volume?
Yeah, so basically if you have two particles and they are this is R1 and this is say R2, the position vectors, then their center of mass is somewhere here, and that's going to be the big R. So if you look at the center of mass, if you look at the center of mass coordinate system, then so you suppose you are in a coordinate system which moves with the center of mass, which is attached to the center of mass, right? Then the relative motion of these two particles is going to be described by this vector. And that is the relative motion that I care about. The interaction energy between this particle and this particle will depend on the relative position of these two particles. It is not going to depend on the center of mass.
So we are considering one interaction only here.
Exactly, yeah, one interaction. Because of that, we can just integrate that out.
Is it possible to consider all of the interactions?
If you take higher order terms, then you'll have to, right? You'll have to take in more and more interactions. If in the series you took higher order terms, then you'll have more factors of F here, and then you'd have to have more and more interactions. And that's why doing higher order terms is going to be so difficult.
Does that mean like 3 particles together and 4 particles together, their interactions?
Yeah, I mean, because it'll be hard to disentangle the interactions in the integrals, right? Like we are able to do at this level. We're going to be able to only, get rid of one of the integrals, but we'll still have many other integrals, and they'll all be coupled.
Sounds lovely.
Yes, lovely and horrible. Okay, let's move on to the rest, the last part.